learn those, please interrupt me and make them, and then we'll address them from there. I've been at UCLA 39 years and have been doing exclusively meteorite research here, so I'm fairly well acquainted with the collection and the displays here. So I want to start with the sun. You know, it's really big. It's you can easily fit the moon's orbit inside the sun. You could fit 1.3 million Earths inside the sun. The sun, as we know, is made mostly of hydrogen and helium. But if we took all, but it has all the other elements too. All the other elements of the periodic table are in there at much smaller abundances. But if we took the hydrogen and helium away, the desiccated husk would still be 6,300 times the mass of the Earth. But minus the hydrogen and helium, nearly every other element would be in the same proportions as in certain kinds of meteorites, which we call the chondrites, and very close to that of the composition of the Earth's mantle. So if we look at that diminished sun and look at the element proportions like the iron to magnesium ratio, the silicon to neodymium ratio, the sodium to potassium ratio, all these other ratios, again, they'd be very similar to that of
I'm sorry because we have 1 p.m. So people are joining us right now. I was doing the grounded tour, so it's okay.
To some extent, and the bulk compositions and isotopic compositions of the big ball of gas and dust from which the solar system was derived. We call that the solar nebula. And these chondrites, which have never melted, they're from asteroids that didn't melt, have been nonetheless modified by some processes on their parent bodies, including some heating, alteration to some extent by water, shock from meteorites impacting the surface. But nonetheless, they are their best examples of what was going on in the early history of the solar system before there were planets. But the point of this discussion at the moment, as their compositions, these chondrites and this desiccated husk of the sun, these are the building blocks of the solar system. These materials, these chondrites, have come together to form the sun, the Earth, the other planets, the moons, the comets, the asteroids, all the bodies of the solar system formed from chondritic material, very similar to these chondritic rocks, which we have here. So we're very lucky to have these samples, these relatively pristine samples, harking back to the era before planets, at the beginning of solar system history, about 4.5 billion years ago. There's different kinds of chondrites. They formed at different distances from the sun. They have somewhat different abundances of volatile elements and refractory elements, depending on, and isotopic compositions, depending on exactly where they formed and what materials came together. But in general, they're from asteroids that didn't melt, some from the inner solar system, some from the outer solar system, and they preserve the compositions that were around at the beginning of solar system history, the building blocks of the solar system. On the other hand, we have some asteroids that did melt. Again, some in the inner solar system, some in the outer solar system. They did melt, probably one of two reasons. The principal cause is probably that of short-lived radionuclides, such as aluminum-26, which has a half-life of 717,000 years, or thereabouts. And if the bodies accreted and came together early enough, they were able to acquire sufficient aluminum-26 to melt in many of these cases. Also, impacts heated the asteroids themselves, which also caused additional heating. I think that there was a combination of the decay of short-lived radioactive elements, like aluminum-26, and impacts, which caused some of these asteroids to melt. So when you melt, the Earth is a differentiated body. It's called differentiated because there are different layers in it. The core of the Earth is a big iron ball. Surrounding it is a liquid iron spherical shell, and we have silicate above it. Silicate liquid and metal and iron metal liquid are immiscible. It's like oil and water don't mix. Metallic iron and liquid silicate don't mix. They unmix. They have to dissolve with one another because the iron melt is denser than the silicate melt. The iron melt sinks to the gravitational center of the body. The silicate melt floats above it to form the crust and the mantle. So just as the Earth has an iron core and a silicate mantle and crust, differentiated melted asteroids have a metal core and a silicate crust and mantle, if you will. The most famous of these is Vesta, the second largest asteroid, and it has a surface covered with basalt. These fine-grained dark rock is the same that we see in Hawaii, covering the Earth's ocean basins. Kilauea is the most active volcano in the world, roughly on average every 2 or 3 years, and that is basalt. If we look at the moon, the dark areas of the moon, the Mare, are basalt, also rather similar in composition to those in Hawaii or Iceland. If we look at Venus, Venus has a lot of volcanoes in it with basalt. If we look at Mars, Mars has basaltic volcanoes on the farthest ridge, Olympus Mons, perhaps the biggest volcano in the solar system. Again, basalt. So basalt was a very common igneous rock from many different planets in the solar system, and asteroids as well. And so if we have an asteroid that melted, we would expect to find an iron core and a silicate mantle, perhaps rich in the mineral olivine, and then a basaltic crust. We see the basaltic crust on Vesta, as I said, the second largest asteroid, plus a few other small asteroids, which might be fragments of Vesta. But there's some meteorites that are also basaltic that are not from Vesta because they have different compositions. So there are other asteroids out there that give us basalt. But also we would expect to find irons from the core. If we look at some irons like this is a big mass of solid iron. Feel free to touch it and hit it with a magnet. This is about 90% iron, 10% nickel, or thereabouts, with smaller amounts of other elements in it, including some sulfur. But these are from the cores of asteroids that melted, differentiated asteroids. These asteroids must have been destroyed by a huge impact after they cooled and formed then the metal core solidified, formed these big iron meteorites over here. We have in some of these cabinets, like over here, and in the one over there, some of these iron meteorites which have been sliced open to make slabs, like this one here, and then polished. And then we can see in many of these things what we call a Widmann-Staten structure, because Widmann-Staten published it second. A guy named Thompson published it first, but he was sort of forgotten. So Widmann-Staten won. But if we look here, we see sort of this cross-hatched pattern in many of these things. You can look at this cabinet, you can look at the ones over there as well. And this is due to the intergrowth of two different iron nickel minerals, one with low nickel called camosite, and one with high nickel called taenite. And they have different resistances to acid corrosion. So when we etch it with acid lightly, you get this pattern that comes out more visibly in many of these irons. And so this is we can't reproduce this on Earth because it takes many millions of years for it to cool and form this pattern. So if you see this, it's very indicative of these things being actual iron meteorites. Okay, that's a really broad overview of the different kinds of meteorites we have here. In addition, we have a few things in the cabinet over there. We have tektites and Libyan desert glass. These are terrestrial materials, but formed by meteorite impact. So if we look at the tektites, there are different strewn fields of tektites here, due to large impacts on the Earth, and we melted wind-blown dust called loss in these things, and then the dust melted. There's different theories as to how it formed. Some of the dust may have been lofted into the air, and then if the air had been heated to incandescence, the droplets may have melted and then formed down to form puddles. And the later tektites, the long tektites that Kevin is pointing to over there, are fragments of these puddles of melt that are on the ground. The splash-form tektites, the others with those funny little shapes, are formed by dust that was melted and then tossed into the air and then it was spinning and formed these different shapes. It was spinning round and round, and you get a dumbbell. If the dumbbell pulls itself apart, you get two teardrops. And so we have some of those tektites over there. There's another kind of tektite that we have not yet put on display, which are called buttons, also from Australia. And these are little droplets of dust which have melted twice. They melted during the original impact. They were held above most of the atmosphere and they melted again coming down. So they have this little flange ring around them as they're coming down. We have some, again, in the collection, but not yet upstairs. We only got them recently. The Libyan desert glass, which is, it's called that because it was found in Egypt. These are, again, chunks of melted quartz sand on the ground. And we can see different layers in them. The different layers they have different colors because they have different amounts of bubbles. And some of those with bubbles, a lot of bubbles are lighter colored, those with fewer bubbles are darker colored in there. And so we have these different layers, very viscous liquid, silicone-rich liquid, that's flowing over one another very slowly. And if you get really compressed, the bubbles might come out. I'm not exactly sure why that's the case. But you actually see some similar things in glaciers on in Antarctica. You can see there's different layers in there. Some are darker and some are lighter. Again, that's also due to the difference in bubble abundance. So we have these things over here. One of our most popular displays is in the cabinet around the corner there, and those are called meteorons because they're not meteorites. And these are things that we've gotten over the years. Every single day, we either get samples or pictures of samples from people claiming that these things are meteorites, and they're not. They almost never are. In the 39 years I've been here, from the general public, I've gotten 56 real meteorites and many, many, many thousands of meteorons. And we have a few of them on display here. And essentially a meteoron, it can be anything. I've gotten gelatin as a suspected meteorite, and machine parts, numbers, and pottery shards, paper, petrified wood. Petrified wood, yes. They found life in meteorites. There's petrified wood. It's going to be meteorite, I can say. And I get about I get emails from about 6 different people every day of the week, claiming that they found meteorites. And I don't know, they beat the odds. They all say that. They beat the odds, and I have to really take their claim seriously because they know that they're meteorites. They've got an hour of research on the internet. And so anyway, so we some of these are really beautiful over here. We have one particular one over here called the it's a green slab made from bronze, I think it was, and they made this and then they threw it on Lake Erie to prevent shore erosion. And then some of these guys found it and they started marketing it as the Emerald Meteorite. And they sent me a piece, and I said it wasn't a meteorite. They said, "Have you ever seen anything like it before?" I said, "No, but it isn't a meteorite." So then they get their hands. Alan Rubin says they've never seen anything like it before. They just forget the second part. But again, it was another meteorite, but a pretty one, so put it out on display. So we have a lot of pretty ones over there. But anyway, the bottom line is that there's a few sources of extraterrestrial material. We have meteorites, which are most abundant source of all. We have a few return samples now from asteroids, and we're getting more. But these are small quantities of material. They're great to have. They're wonderful to have, so we can actually know exactly where they came from, which is very helpful, unlike the case for most meteorites. But their total abundance is pretty low. We have moon rocks returned from the Soviet Luna missions, the Apollo missions, and now a couple of missions from China. Again, but very limited quantities of material. They're great to have. We know where they're from, which is very helpful, but they are the most abundant source of meteorites, which they come to us for free. We don't actually come to Earth for free. We don't actually get them at UCLA for free. In most cases, we have to buy some or trade some, or we have a deal with a lot of meteorite dealers and collectors that they have a sample and they want to sell it, but the commercial price depends on what kind of a meteorite it is. And so they need someone to characterize it for them, someone what kind of meteorite it is. And so the price could vary from $2 a gram to $2,000 a gram, which is a tremendous difference. And so we get some of the samples here, many of the samples, hundreds of samples in that collection came from us characterizing the samples for dealers and collectors. Then we get a piece for our collection in return for our services.
So we've also gotten donations.
And we got the donations, yes.
And there's some on loan. Some of these big irons are on loan.
From where?
From individual
Yeah.
private enthusiasts,
Private collectors, yes.
private collectors.
Private collectors with money,
Right.
because it's an expensive hobby. And we've gotten, this is a donation here from the Schlazers.
This one is from this is on loan from the Smithsonian. Very cool.
Right. And some of these are on loan from a private collector, as is that huge chondrite over there in the corner, which is not yet characterized properly. And we've gotten more donations recently, which we're going through right now. We're trying to characterize them properly. So yeah, people give us donations from time to time, and so yeah, the collection grows that way as well. Okay, but I'm happy to answer any questions about the science or about the collections, and Kevin can also address these as they may come up.
So they said one of the techniques that they used to try dinosaurs because they found the layer next to something in Italy, right? They separated the layer of limestone with fossils and the layer of limestone without fossils that had been a mass extinction. And they analyzed the layer of soot and decided that came from an impact by Aztec. Can you elaborate?
Yes. Now there's over 100 sites, maybe 150 sites on Earth that show this little layer of dust.
If it had just been in Italy, it would not be that. It would be interesting locally, but not globally.
Yeah, there's now, I think, probably 150 sites of this. And now let's think of the Earth. When the Earth melted, not only iron and nickel went down there, all the other metals like osmium, iridium, platinum, palladium, almost all those things went down into the core. So the abundance of, let's say, iridium, to pick one randomly, is very low under its crust. So when they examined this, did a core, and examined this layer, it was very high in iridium relative to the background. And so they said, some extraterrestrial source had to provide the iridium. And eventually it was concluded that it was an asteroid because we found soot there as well. They found tsunami deposits now in South Dakota recently that have all sorts of jumbled fish and things like that, which was created by the impact. And we actually have a crater now on the Yucatan Peninsula in Mexico. Chicxulub is the name of the crater. And 66 million years ago, an object about 10 kilometers across, as estimated, hit the Yucatan Peninsula in Mexico, created an enormous crater there, put up so much dust and debris into the atmosphere that we had essentially like a nuclear winter for some period of time. Sunlight was blocked out, plants died, herbivores, plants died, the carnivores ate the herbivores, we think the plants died. So we had these mass extinctions. The mammals were around at the time. Some of those species went extinct as well, but some survived because they were small and they were able to either squirrel their food away, no pun intended, or they were hiding burrows. So they had a better chance of survival. And the ecological niches that the dinosaurs had occupied were now vacant, so they were able to proliferate after 66 million years. But yes,
Basically, I think if you were bigger, if you were larger than a large dog, you didn't make it through the impact. Not just you, but every living relative, right? That's what it means to be a species go extinct. So it's quite a traumatic event, and we would not be having this conversation if we weren't hit by this asteroid 65 million years ago.
No, all the non-avian dinosaurs,
Right.
birds survived, but every non-avian dinosaur, even little ones, even chicken-sized dinosaurs, they're all perished.
Yeah.
So
There's a really good nova I saw recently came out. It's a 2-part nova about the Hell's Creek, it's called, in the Badlands or in South Dakota.
Oh, yeah.
It's a well done thing showing them, basically they think they really have probably evidence of the day of the impact.
Yeah.
So the last few hours of the Cretaceous, right, preserved
But I
there.
have a question, why is the region like spread all over?
Because there's dust that went to the atmosphere.
What happened? So, okay, so when the
It's
asteroid,
vaporized, right?
the whole asteroid
Yes.
vaporized,
Well,
but it still created a crater?
It's a huge crater.
well, no, yeah, it's just the impact. The impact created the crater. The asteroid vaporized upon impact. So the energy was still there to make that huge crater. And then a lot of the dust, of course, most of the dust was terrestrial dust, but the asteroid also got vaporized and comminuted and then spread into the stratosphere, which distributed over the globe, and then it fell down. There's actually very likely a piece of this asteroid upstairs that killed the dinosaurs. One of our colleagues, Frank Kite, was doing deep sea drilling in the Pacific, and he drilled through the layer, that iridium-rich layer there, and found a 2.5 millimeter size, highly weathered carbonaceous chondrite, meteorites. And it's every other particle is tens of microns in size or something like that. This was thousands of times bigger than anything else. very far from shore. It's a meteorite, very similar to what we think was the composition of the object which created the crater and killed the dinosaurs. And there's nothing else nearby, and it's at exactly the right level, so it's likely a chunk of that asteroid.
Of course, it's completely altered by
Oh, yeah.
seawater. It's been at the ocean floor for 65 million years, right? But, you know, when we say that everything vaporizes, it's not quite true, everything, right? So, for example, these ones that made Meteor Crater, right? The incoming meteoroid, right, was the size of this building. And these are the surviving pieces of shrapnel that came off the back, who knows, you know, as it came into the impact. Most of the stuff vaporizes because it's got so much kinetic energy, right? The velocities are so high.
But when the asteroid hits, it creates this reverse wave, a reverse vacuum wave through the body, and then swallows off the back of it. So when that stuff hits the ground, because it has other energy going in the opposite direction, it hits at a much lower velocity, so there's much better chance of surviving.
I mean, with things like the Chicxulub impact, it's hard to wrap your head around, but one of the ways that you can sort of get a sense of the impact is that when the asteroid, you know, first hit the ground in the Yucatan Peninsula, the other end of it was still essentially in space, just at the top of the atmosphere. Right, it's that big, bigger than Mount Everest, right? So it's, yeah, 10 kilometers, right? So if you think about it like that, you get an idea, a mental picture. It's not like what we see, like, you know, in the movies with a fireball and something hits and explodes. No, it's
Like a mountain.
it's yeah, a mountain, a huge mountain hits the earth, and you know, there's a flash of light before anything else happens, right? And a lot of it does evaporate, and you know, causes a worldwide climate catastrophe. So it's a fantastic thing.
What is it? Volcanic concentrates.
Well, the temperature of the whole.
This is the combination of the asteroid. There was a shock wave that went all the way from there.
Yeah, people said that. Well, on Mercury, we have some disturbed terrain antipodal to the large base. So it's possible that you could focus the shock wave from there. So it's possible, but it hasn't been as well established that that's the case.
Right.
We had a lot of volcanoes triggered on the other side of the Earth by the impact. It's a hypothesis that we take around it, but it doesn't. There's no.
You have to appreciate the timing. Getting the precision on the timing is very difficult for something that far in the past, right? So, and that makes a big difference.
I think the estimates on Chicxulub that is about 100 million years. So I'll say for another 30 million. You know about statistics.
You guys know about statistics, so you decide. I mean,
So you throw a die, you got 6. Does that mean the next time it's really unlikely to get 6? No, it doesn't mean that at all. The
on the order of 100 million years, we think, right?
yeah, they have this so-called
We
filter.
don't have a very.
On average, over many billions of years, an asteroid that big will hit about every 100 million years or so. But of course, that's and there's a lot of uncertainty in that because the flux now is not the same as it was 4 billion years ago.
Right.
A lot of the stuff's been cleaned out, and so as the years go by, or as the eons go by, the number of large impacts you'd expect would be diminished somehow.
But this would be a good argument, for example, to go back to the moon and really study the moon as a geologic object, not only to learn about the origin of the Earth and the moon, which is certainly great deal of work to do there, but also to get a much better estimate of the recent impact flux. People have been doing this also from orbit, looking at even recent craters, but there's a big gap in our knowledge because we're trying to understand things over very, very long time periods, right?
But can you tell on the moon, for example, if they go and bring you from every crater, like a sample from the rim, can you tell like the age of when the craters were formed and all that?
It's complicated. It's a whole. The moon has been getting whacked for 4 billion years, right? So it's a complicated thing. But I guess my main point is, the Apollo program, which ended 50 years ago, right? was not a systematic survey. They went to the near side, equatorial region on the near side of the moon because of astronaut safety.
And they
Right.
just brought pieces.
And they brought, wherever they landed, they brought stuff back. And in the later missions, they actually had, you know, a little dune buggy and stuff, and they could explore a little, but still. I mean, you know, if I said you could go to 6 places on the Earth and you could fill a sack with rocks, now tell me the history of the Earth, okay? This is a hard problem, right? Oh, you can only be there for a day or two because you got to carry oxygen with you and stuff like that. So,
And in addition, you know, we use isotopic systems, particularly Kevin and his colleagues do that, to measure the ages of these things, but these things have been disturbed since they were formed. Other impacts have come in and heated it up and releasing some other, so it is pretty good. Yeah,
So a number of years ago, went on a trip to Hawaii. And on top of Mauna Kea, visitor center, very nice visitor center. I bought a few samples. You know, who certifies those little meteorites? This? Otherwise, not a meteorite.
buyer beware.
No, well, they're-
Caveat emptor.
you can buy a lot of meteorites on eBay,
Yeah.
and
Most of them are.
and most of the things we sold on eBay, not all by any means. I do.
The next word.
So I've classified many hundreds of meteorites, and not just me, but there's a lot of other people around the world that do the same thing. I'm retired now, and I don't do it as often as I used to. But you know, the typical method is for things to be brought to a meteorite researcher who goes and analyzes it, and then says it's this kind of meteorite, and then it's published online in something called the Meteoritical Bulletin Database. And then it's certified, and it's official, and then the collectors can sell it for whatever the commercial market is for that particular kind of meteorite. And those would be real meteorites.
Can I click mine over?
I heard that a lot of the nickel that is in nickel was somehow formed by, in the United States, nickel was formed by an event. Are you anything about that?
Well, in the Sudbury Basin, in
Okay.
Canada, there's a layer called the nickel eruptive, and various papers through the years have said, yes, this nickel is from an iron meteorite. Various papers through the years have said, no, it's terrestrial.
No, but it's not just that the nickel is from the iron meteorite, probably not. It's that it caused an impact now.
Right.
Or differentiation. So it was a very large mining operation, if you will.
So it's probably terrestrial nickel,
Right.
but it is an impact basin, which triggered volcanism from there.
Sudbury.
Sudbury, Canada.
In Ontario, right?
It's-
Right. Other questions? Yes.
So I read somewhere that they think that the Permian extinction was also caused by a meteor impact. Do you know anything about that?
Yes, we know about that. There's no consensus on a meteorite causing any extinction other than the implications.
Right.
People have said, essentially for every extinction, there's been a paper or two that said, oh, it impacted, but the evidence is very scant. And so the most of the paleontologists and evolutionary biologists would say that these other extinctions were caused by other mechanisms than impacts, whether it's volcanism or climate change or whatever. But most of them are not thought to have an extraterrestrial cause.
It is helpful that the and Cretaceous impact is the last big mass extinction, right? So the further you look back in time, the murkier things get, right?
But some of them are very localized, so it makes sense, actually. If it, you know, climate change is something more global, but if you have a localized extinction.
Well, these we're talking about mass extinction.
Talking about mass
Yeah, no,
extinctions,
I'm not
where
talking about the
most
because
likely
there
are-
are some small-
right? Yeah, but it's hard to imagine a meteorite impact making a small extinction, right? Because then you would have to have a very localized population of flora, fauna, whatever. And would be very bad luck. Could happen, but yeah.
With that, wasn't there something recent about
Oh, there's always papers like that. Every couple of years, someone tries to say that these cities, Sodom and Gomorrah was an impact, and they always try to reconcile the Bible and things like that with extraterrestrial events. But let's just say there's no scientific consensus that any of that happened. It's pretty unlikely.
Excuse me, can someone repeat the question?
Okay, so you mentioned composition of solar system material. Has there ever been found a meteorite that has perhaps a composition that indicates it might be from outside the solar system?
That's an excellent question. No. You're
going to talk about three solar grains, right?
Well, I was. There have been a couple of interstellar interlopers, which have gone through recently, the last few years, they've gone through the solar system. One's a real, just a regular comet, and one is an elongated chunk, which some people think is nitrogen rich, but it's not really clear what it is. It was seen on the way out. So those are parabolic orbits and are not part of the solar system. Recently, there was a confirmation that a fireball seen in Papua New Guinea came in at such a high velocity that it was also in a hyperbolic orbit, probably extraterrestrial. So the possibility exists that there'd be an extraterrestrial meteorite. But as Kevin wanted to jump in, there are three solar grains. These are tiny little grains, micron size up to 10 micron size, which are from other stars. They form in the atmosphere of other stars, supernovae and red giant stars.
So, and how do you know that?
Their isotopic compositions are totally different than that of solar system material. Totally different from the sun, the earth, all the bodies that we have, just really different. We find them in primitive meteorites, these carbonaceous chondrites, and then we go and essentially dissolve them, and the grains that are left are originally these grains that were left were very refractory, and as the Sky University of Chicago once said, how do you find a needle in a haystack? You burn out the haystack, and the needles are left. And so that's what they did originally, but now on some super machines, you can go and just look at thick sections or thin sections and take essentially an image of it in different isotopes, and you can see that these grains have different isotopic compositions. But I'll let Kevin, since Kevin has worked on this a lot, I'll let him go on. Go ahead.
I missed what you just said.
No, but go ahead. Go ahead.
No, go ahead. Question about
Start anew. What are free solar grains?
Well, free solar grains are microscopic rocks that condense in the outflows of dying stars elsewhere in the galaxy. And by luck or whatever, they managed to get into the mix of stuff that formed our solar system. Most of that material is locally processed, and either because of the properties of these grains as being very tough things, like silicon carbide is one of the main ones that survives, that they have found their way into meteorites. You are surrounded by, especially over in that cabinet, you are surrounded by little grains of stardust that would have formed 5 billion years ago around some other star, or as the star is dying and shedding mass. And they're in those rocks, but they're not very abundant in there. They're at the sort of part per million level, and it takes some sophisticated methodology to find them. And then what we can do is study their isotopic properties, which informs us about the nucleosynthetic properties that are going on in different stars. And we can do this on a very, very minute, a very detailed basis, whereas astronomically, you're looking at more of a statistical basis of certain types of stars doing certain kinds of energy generation during the evolution of their life, right?
So there's differentiation inside the body, does that mean isotopic properties?
If one of these grains got into a planetary melt that would differentiate, it would destroy it. So you really find them in the chondrites, because those are sediment, they're not melted, they're sedimentary garbage cans from the solar system. They're sedimentary rocks of things that accreted to the surface of some asteroids and got lithified in ways that we don't fully understand, and then made their way to the Earth because of some impacts and some resonances. I'll talk a little bit about that when I talk about asteroid sample return in just a few minutes, but you know,
How do you distinguish between those dust and the other stuff? I mean,
by its isotopic properties, because what stars do,
what machine, like, not a
oh, you use a mass spectrometer. The best mass spectrometer for doing this is one that has microscopic capabilities, so you can do both. But you can measure the isotope ratios, because stars are nuclear reactors. They change the isotopes, right? That's what the sun is doing now. Not in a very interesting way for rocks, because it's just turning hydrogen into helium, and neither one of those make rocks. But other more massive stars do more interesting things, and very important things for us, because, right? Because everything, you know, the iron in the hemoglobin in your blood is made in the supernova, right? So you are made out of stardust. And this is the oxygen, everything, right, all of these things. So, yeah.
You know, when a meteorite impacts the Earth, does it leave a unique magnetic signature that's detectable?
On the Earth?
Yeah.
I don't think so. The Earth is big.
But I mean, like, in a localized area, will it?
Well, people have suggested that meteorite impacts on the moon and some other places have created a magnetic field in some of the surrounding rocks, but it's really low compared to the Earth's magnetism. And so it'd be hard to find. Phil Bland has worked on some of this material.
You know, like using certain methods, maybe like to do something from that. You know.
Certainly on asteroids, things can happen like that. But the Earth, you know, the Earth's magnetic field, first of all, is very complicated, but it's generated way below our feet, right? So it's hard for anything that happens on the surface to affect the source of what's going on in the outer core, right? So if you think about it like that, it's very, you know. Now, you get something like a moon forming impact, that's a whole different thing, right? But that's not going to happen. Right?
People have suggested years ago that meteorite impacts affected the Earth's gravitation, magnetic field. Billy Glass suggested that, but no one believes it. But people have made that suggestion. But
So on, I guess astronomers look at asteroids out in the solar system, they get their spectral time.
Yes.
Is there a good understanding from what these rocks have? Is there a connection of we know what all, and is there an asteroid type, spectral type that you haven't found a meteor right from? Or?
We're getting better at that, so I'm going to talk about that in just a bit. But the short answer is yes, there are correlations, and yes, they're partly understood, and we'd like to understand them better.
And yes, there are asteroid spectral types that don't seem to be correspond to meteorites in collections.
Mm-hmm. Okay, I don't know what kind of schedule we're on here, so and we don't see Ken.
It's 2:12.
Wait. So we go to so it's at 3. So Professor Vasilis Angelopoulos is here, everyone. And so he's going to, after my talk, and we'll have a little Q&A, he's going to introduce a new initiative at UCLA, which is called the Space Initiative. And also, we can have a short tour of the Elfin laboratories, where we had students at UCLA who built a CubeSat, and it's circling the Earth now. And so I thought that might be interesting.
We can have some Q&A.
We can do, yes. We're, yeah. But thank you, Alan. This is.
Okay, thank you,
great,
guys.
Yeah. Okay, we're going to go back to the conference room. So if you haven't been there yet, just follow the crowd.
It's the Kevin McKeegan show coming on soon.
Right. Thank you, Alan.
So I don't, get people dizzy walking back.